Here's our next exhibit. So we have our incline with an angle theta. This time we have two masses, or two objects I should say. We have this one on the actual incline, and then we have one hanging off of the end. This should remind you slightly of some of the problems we've done before, like Atwood's machine or the tabletop with the one hanging, except this time it's not horizontal, I have an angle. So like those other problems, there is a frictionless pulley. The pulley is frictionless. They are attached by the same string. Now, what this implies is the following. One, the tension is the same for this string because it is only one string. And two, the whole system of both blocks being together, held with the same string, means that they'll both be accelerating at the same rate. However, while this may be accelerating on the x-axis, this may be accelerating on the y-axis, or the other direction. Don't ever take for granted that one block looks bigger than the other one, okay? Or let's say you have numbers, right? And let's say this is 21 and this is 20. Don't take those numbers for granted either. You have to just be careful with your setups, be aware, and just because the shapes look bigger doesn't mean anything. There's an idea called density, and you could have a small object with a high amount of density and therefore has more mass as a result. So we're going to throw a few things at your way. We're going to assume this is a second law problem, so there will be acceleration. And we're also going to assume that there's friction between this block and this plane. The pulley remains frictionless, but the plane and the object that is resting on the plane will have friction. We'll start off with a hanging mass. And for the record, we'll call that one M2, and the one on the top will be M1. For M2, we have an easy time identifying the forces. There's a tension going up, and there's a weight going down. And we need to pick an acceleration. So this is a very, very, very important side note. Since we weren't given any actual numbers or any general ideas of what's going on, we have to take a leap of faith and decide which way this is going. So I could either assume that this is going up, accelerating upwards, or it's accelerating downwards. But I can't pick both. I must pick one and stick with that resolve all the way throughout the problem. What are the implications of us picking the wrong direction? Well, the physics doesn't lie to us. So if we do everything correctly mathematically and we happen to pick the wrong, let's say I picked it as going up, and I set everything up like that, and that would also assume that this is going down to the left. And if I do all my math and I do everything correctly, and at the end I get a negative answer, then the physics just revealed to us that we picked the wrong direction. It doesn't mean you have to redo the whole problem. It just means we set up everything in the opposite direction. And so if we get, for example, an answer of negative 2.3 meters per second squared, and we did everything correctly, it just says, oops, we went the wrong direction. So we should have gone down instead of up. It doesn't mean do the problem again, it just means, okay, so the answer is 2.3 meters per second squared. Okay? For this problem, just for the heck of it, I'm going to assume that up is positive and down is negative. No particular reason, just gonna do it and see what works out. So if up is positive, that means I have tensions going up and I have weight going down. That's M2 times G, and that's equal to M2 times A. And I leave that alone. That's done. And that was our setup for the hanging mass M2. For M1, we have, of course, the weights going down, straight down. The normal force is perpendicular, and do your best to try to draw the same length as a weight. They are obviously on a different angle, but they should be the same length. I have a kinetic friction going this way, and it's only going this way because I'm assuming that the acceleration is going in this direction, right? We said we made the assumption that this one is going up, so therefore if this one's going up, this one must be going down. If instead we had assumed that the acceleration was going in this direction, then the friction is always opposing the direction of motion. But in this case, I'm assuming it's going down the ramp, therefore friction opposes it and goes up the ramp. This is our setup so far. If we set up our X and Y axis, it aligns nicely with the friction, so I don't have to worry about any trigonometry for that. Or for the normal force, it's the weight that's giving us issues. We'll need to do some components for that, an X component and a Y component. We'll need the angle, we'll need to set up sine and cosine, and do a little bit of that setup. For now though, since acceleration is going down, I'm going to assume this way is positive and this way is negative. A couple of good habits that I can strongly suggest to you as a new learner of physics is to pull out the colors. So if you're not doing this in different colors, you should. It helps you to keep track of things better. Also, a big faux pas or a big mistake that students tend to make early on with this is they don't draw these triangles right. I've seen too many kids draw it like this and then do it like this, and then they tell me this is the right angle. And then everything gets set up really wrong. Remember that this goes straight down and it's opposite and equal to the normal force. And then from here I go straight this way and the right angle is formed right here. This angle theta is going to be this angle theta right here. This is my WX. The hypotenuse is W. We do some trigonometry. And we get that the opposite of this angle is WX, so sine theta equals WX over the hypotenuse, which is W. And again, if we're at this angle right here, that angle being the Greek letter theta, the adjacent is WY, and the hypotenuse is W. If you're very far removed from trigonometry or for whatever reason, we never do sine or cosine from the 90-degree angle. After some simple algebra, where we multiply the top by W, and this by W, and this by W, and this by W, that way they cancel out, we get the following relationships. Now, do not ever assume in physics that things are always the same. So just because you see a problem like this doesn't mean you're going to go ahead and automatically make things cosine and sine. Though WY is going to be cosine, Mr. Rover. The WX will always be sine. You're going to see a couple of problems where they may not, depending on which way the force is approaching this object. So always be on guard with the trigonometry and do your best to always set things up from scratch. Let's go ahead and set up Newton's first law. But Mr. Over, this is a second law problem. Silly people. Is this thing jumping up and down on the y-axis? Is this box jumping up and down, accelerating up and down? No. So unless if it's jumping off of the plane or if it's sinking and drilling itself into the plane, like literally displacing itself into the plane, then we don't do second law for the y-axis. We're going to just be doing the first law, and that's equal to 0 to show the balance. If I pick up to be positive and down to be negative, I have the normal force that's going up, and that's opposing the WY component, which of course I can write as normal minus m times g, and this is, by the way, m1 times g times cosine theta equals 0. And in a similar manner, we could go ahead and just write this out as n is equal to m1 times g times cosine theta, which tends to be the more useful and popular form of this. In general, this is generally what's going to happen with the y-axis for an object on the plane at an angle. In general, okay, there are some cases where extra things would be happening, but in general, this is pretty typical. We now turn our attention to setting up the second law along the x-axis for the first object. Now, the process in which I did this problem, in this particular problem, is actually hopefully beneficial to you. So usually I go for the easier things and leave the last the most difficult for the end. So doing the hanging object, we've done that many times in this class. That's the first thing I did. Next, I did the y-axis of the object on the plane, which ends up being first law typically. And so we tend to see a pattern of repetition there. And then we'll leave second law at the end, because second law is always the big equation that tends to change from problem to problem. So let's look what we have here so far. And we are missing a force. Did you catch it? There should be a tension going in this direction, right? That tension that was shared by the string. So we technically have three forces on the x-axis. We have the tension going to the left, which is negative. We have the friction, the kinetic friction going to the left, which is negative. And we have this x component of the weight going to the left, which will be positive. So I have, I'm going to just write this officially as m1 times g times sine theta, because that's positive, minus the tension minus the coefficient of friction is equal to m1 times a. So now this is definitely, second law is along the x-axis is where you're going to see a lot of variability in your setups. And furthermore, we should note that the kinetic friction can be written as the coefficient of kinetic friction times the normal force. Now, of course, the normal force is right here. So then we can incorporate this normal force equation in place of the normal force here, and we get this monstrosity of an equation. Now, as horrible as this looks, in actual problems that you'll be given, most likely you'll be given values and numbers and units. You can then plug those in and things will collapse and combine and give you a lot simpler equations. And then you're going to go ahead and solve appropriately for acceleration or for t, noting that both of these have the same acceleration, right? And both of these have the t's. So we do have three systems of equations. However, this normal force equation ended up being implemented in here. So technically, we no longer need this anymore because it's been implemented into this equation. And we end up having to just work with this equation and this equation. Two equations to solve for two unknowns.